All right, guys, in this video, we're going to talk about how to calculate the pH of a weak acid solution. If you recall, on the previous video, we talked about how to calculate the pH of a strong acid. For a strong acid, all that you had to worry about was to think about the concentration of the acid, which would directly translate to the concentration of the hydrogen ion because all of the acid dissociated. For a weak acid, we actually have an equilibrium where both the molecular acid, which is neutral, and the dissociated products of the acid are present. So the concentration of the acid is not going to be the same as the concentration of the hydrogen ion. So we're going to talk about how to go about that. To begin with, here's a comparison of what a weak acid behavior is compared to that of a strong acid. On the left, we have a strong acid. Remember that a strong acid, whoops, sorry about that. Let me fix my pointer options. All right, so a strong acid is one that completely dissociates. So if we have our strong acid, which we're calling HA in this case, that HA is going to completely dissociate into H plus and the corresponding anion, which is A minus. So H plus plus A minus. So all of the acid does that. And you can see that in the representation here. Notice that all that we have is the anions that are by themselves, and the H plus that has been released has associated with the water that surrounded it in order to form hydronium ions. Notice that there's no molecular acid HA left. On the other hand, if we have a weak acid, that weak acid only partially dissociates, which means that if we started with HA, some of it would be in the form of HA, and some of it would have dissociated into H plus and A minus. This is an equilibrium process indicating that all these species are present. And you can see that in the molecular representation here, where some of the acid is in the molecular form, where the HA is combined, and some of the acid has dissociated into the anion and the respective hydrogen ion, which has combined with water to form hydronium ions. The next slide shows you a list of various weak acids together with their structural formula, their conjugate base, and a property known as Ka. We'll talk about Ka in a little bit, but I don't need you to memorize anything on this list, but I do want to point out that I want you to remember that hydrofluoric acid is a weak acid. I get a lot of people that confuse it for a strong acid since it is very similar to hydrochloric acid, HCl, or hydroiodic acid, HI, right? So remember that HF, hydrofluoric acid, is a weak acid. Another thing that I wanted to point out is that we talked about organic acids that contain this carboxylic acid functionality, COOH. We had specifically talked about the example of acetic acid or CH3COOH. And I do want you to remember that anytime that you see this designation of COOH, that is indicating a weak acid. And then the other thing that I wanted to mention is that the Ka value is basically talking about the equilibrium constant for the acid dissociation. That equilibrium constant is just like the other case that we had discussed before, the Kcs or the Kps or the Kws. Is basically the ratio of the products to the reactants, each of them raised to their own coefficients. And we'll get back to Kas in just a little bit. Now, here is just to remind you about the carboxylic acids. This is an example of acetic acid again, CH3COOH. Notice that only that hydrogen, only that one hydrogen in the COOH is acidic, meaning that that's the only proton that can be donated out of that molecule. I also want you to identify the fact that if you have COOH, that's not showing a hydroxide, right? Remember that hydroxides are OH minuses. They do not go with a COOH, right? That's different. A hydroxide is indicative of a base. COOH is indicative of an acid. And here are two examples, acetic acid and benzoic acid. All right, so coming back to Ka, that's the weak acid dissociation constant. The strength of the acid is ranked by the value of the Ka, or the value of its dissociation constant. For any particular equilibrium of a weak acid that dissociates into hydrogen ion and the respective anion, we can represent, or we can write the Ka as the ratio of the concentrations of the products, which are the hydrogen ion and the respective anion, divided by the concentration of the reactants, which in this case is the concentration of the weak acid. At equilibrium, each of these would have their own concentration depending on the problem, and that Ka gives you some information. Basically, the value of the Ka, if it's large, it would indicate that more of the acid has dissociated because you have more of the products, more of the H plus and the A minus, and lower amount of the molecular acid. That would tell you that in fact you're dealing with a stronger acid. I'm not saying a strong acid, it's just a stronger acid than a different acid, than a different weak acid, I should say. On the other hand, if the Ka is small, like really small, then that means that there's more of the molecular acid. That means that more of the acid has stayed in this form as opposed to dissociating into the ions, right? So that would indicate a weaker acid. So if you are comparing two different weak acids with different values of Ka, the one that has the larger Ka would be the stronger out of the two. All right, so here we're gonna do an example in which we're going to rank the acids from the highest acidity to the lowest acidity. Go ahead and pause the video and see if you can answer it yourself. Da, 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 da. All right, so if you came back now, what we need to do is to rank them from the highest acidity, which means the highest Ka. Oh, my thing is not working. My pen is not working. To the lowest acidity, meaning the lowest Ka. So, ooh, of course, in this case, the answer is going to be number 2, because hydrofluoric acid contains the largest out of the 3 Kas, and acetic acid, HC2H3O2, has the lowest Ka. Just to remind you, negative exponent here, which is like a smaller number, that actually indicates a larger number versus something that is 10 to the 5, for example. All right, the next thing that I want to introduce is the concept of percent ionization or percent dissociation. This is a variable that is useful in order for us to specify the amount of weak acid that actually has dissociated out of the starting molecular acid. The percent dissociation or percent ionization is defined as the ratio of the concentration dissociated versus the initial concentration of your acid, and multiplied by 100 in order to make it a percentage. At the same time, we could define it as the concentration of the hydrogen ion at equilibrium divided by the concentration of the initial weak acid times 100%. This equation is the one that you would utilize, for example, if you have used an ice chart. Once you identify your value of X, the value of X would represent the hydrogen ion at equilibrium. And so you can plug it in here and divide it by the initial concentration of the acid in order to find the percent dissociation or percent ionization. All right, let's do an example. So the question is, lactic acid has one acidic hydrogen. That means that I can represent it as HA, where H is the hydrogen ion that is acidic, and the A represents the anion. So I don't actually have to write this whole molecular compound. I can just call it HA. A 0.1 molar solution of lactic acid has a pH of 2.44, and the question is, calculate the Ka for this substance. So I'm going to go ahead and escape from here and go into a separate page where we can do the problem, hopefully. So let's come here. Okay. I want to, oops, I should have done this before, but I didn't. So I'm going to go ahead and add a layer. Okay, sure, go away. And let's see. All right, am I able to write now? Please tell me that I can write. Yes. All right, so lactic acid has one acidic hydrogen. We have a 0.1 molar solution of that acid, which has this pH. The question is calculate the Ka. So what I'm gonna do is I'm going to write my equilibrium equation. So HA, which is my lactic acid, I know that this one dissociates partially, which is an equilibrium process, into H plus the respective anion A minus, or in this case, the lactate anion. I'm going to go ahead and set up an ice chart. And I know that I need an ice chart because in the end, I need to find my Ka. And I know that my Ka is going to be the concentration of hydrogen ions times the concentration of the anion, because these are my products, divided by the concentration of the starting acid. All of these at equilibrium, since Ka is an equilibrium constant expression. And I don't have any information about my equilibrium concentrations because what I'm given is the concentration of the initial acid before it has dissociated. So I know that I need to set up an ice chart in order to find out what are my equilibrium concentrations. So I come back here, I set up my initial, my change, and my equilibrium. For the initial acid, I do know the concentration, which is 0.10, come on, period. And I know that initially I have no products of the dissociation. I then set up my changes. So in this case, my change is going to be negative X for the acid because I know that the acid is only going to decrease in concentration as it forms some products. And my products are going to be positive because they're going to be generated in this process. And then from there, I just do the sum of each of the columns. So 0.1, oops, 0 minus X, and then this one is 0 plus X, which is X, and 0 plus X, which is X. All right, so obviously I don't have enough information in one column to solve for X yet. So what I'm gonna do is that I'm going to come here and I'm going to, well, I'm gonna go ahead and think about, I'm gonna go ahead and substitute the equilibrium line into each of these concentrations. So here for hydrogen ion, I have X. For the anion, I have X. And then on the bottom, I have 0.1 minus X. Of course, I don't know the value of X and I don't know Ka. So here I want you guys to think about, what other information do you have that would help you either find Ka or find X? And if you notice, the other piece of information that we do have is the pH of the solution. The pH is related to the hydrogen ion concentration, and more specifically, to the hydrogen ion concentration at equilibrium. So what I'm going to do is that from the pH, I'm going to go and find the hydrogen ion concentration at equilibrium. And that is basically equal to X, because if I come back to my ice chart, you can see that X is the hydrogen concentration at equilibrium. Okay, so how are we going to go from pH to hydrogen ion concentration? So if you remember in the previous video, we had done a calculation where the hydrogen ion concentration is equal to 10 to the minus pH. So that's what we're going to do. In this case, 10 to the minus 2.44. And that gives us a hydrogen ion concentration at equilibrium, which is equal to 3.6 times 10 to the minus 3. 3.6 times 10 to the minus 3 molar. Again, make sure that you guys are being able to do this in your calculator. And if you have any questions, send me an email. And now that we have the hydrogen ion concentration, according to our ice chart, this is equal to X. So now all that we have to do is to come back to our Ka equation, replace x with 3.6 times 10 to the minus 3. And of course, this is equal to x squared divided by 0.10 minus x. So Ka is equal to 3.6 times 10 to the minus 3 squared divided by 0.1. Sorry, my pen is writing really slow. If my computer is about to die. Minus 3.6 times 10 to the minus 3 is 0.0036. And that should give you a value of 1.3 times 10 to the negative 4. We are done. All right. So then we go to the next slide, which I believe is the next problem, which is to calculate the pH from the Ka. The question is, actually, let's go ahead and go back to this program where I have already written it down. So calculate the pH of hydrazoic acid in solution. The acid dissociation constant for Ka for this acid is 1.9 times 10 to the negative 5. All right, so let's start with part A. It says calculate the pH. Remember that this is a weak acid, so we cannot just take the negative log of this concentration because this is the concentration of the starting acid. Once it actually dissociates, only a part of that will become H+, and we need to find out what is that part. So what we're gonna do is that we're going to set up an ice chart again. In this case, we're gonna call our hydrazoic acid just HA, if you don't mind. That just represents a weak acid with one hydrogen ion that we are donating. I'm gonna go ahead and say, okay, I have HA, which is going to partially dissociate, indicated by the double-sided arrow, into H+ and the respective A- anion. I'm gonna set up my initial, my change, and my equilibrium. We were provided the starting concentration of the acid. That's going to be the initial here, which is 0.175. We can assume that initially we have none of the hydrogen ion and none of the anion because those are going to be formed as the acid dissociate. We then set up our changes, negative X for the acid, positive X for the products because those are being generated during this process. And then we don't know any information about the products at this point, about the equilibrium at this point. So I'm going to go ahead and just add the column, 0.175. My period did not write again. That's 0.175 minus X. Again, my computer is trying to die. 0 plus X is X, 0 plus X is X. All right. We do know the value of Ka. So what we're gonna do is set up our Ka equation, which in this case is going to be our hydrogen ion concentration times our anion concentration divided by the acid concentration, HA. We're gonna go ahead and replace it with the equilibrium line, which is X and X. So I'm gonna call it X squared. Those are my products, X and X, divided by the reactant HA, which is 0.175 minus X. All right. Now, we know that the value of the Ka is 1.9 times 10 to the minus 5. I wonder what could we do in order to simplify the math? Because if I go and I multiply my denominator to this side, then I'm gonna end up with a quadratic equation. Well, if you recall, we talked about this in the last chapter, and we said that if the value of the K was very small, we could go ahead and assume that the X from the change that we were either adding or subtracting could be assumed to be very, very small and neglected. So we're gonna go ahead and assume that. So assume that the X is very small, and that's going to simplify our math. And if you don't mind, I'm going to continue here. because now we can say that Ka is going to be equal to x squared divided by 0.175. And that makes our math a lot easier. And of course, remember that Ka was 1.9 times 10 to the negative 5. Therefore, x squared is going to be equal to 0.175 times the Ka, which is 1.9 times 10 to the negative 5. And let me see if I can find my notes. Any minute now. According to my notes, x squared is equal to 3.3 times 10 to the minus 6. And therefore, once we take the square root, x is going to be equal to, my hand is falling asleep, 1.8 times 10 to the negative 3. All right, so we have x, but we were not being asked for x. We were being asked for the pH of the solution. Once we have x, notice that x represents the hydrogen ion concentration at equilibrium, which is very important because now that we know the hydrogen ion concentration in our solution, we can get ahead and use it in order to find the pH. We know that the pH is defined as the negative log of that hydrogen ion concentration. And so that's what we're gonna do. Sorry, my writing is way delayed. All right, so finally, pH is equal to the negative log of the hydrogen ion concentration, which is 1.8 times 10 to the negative 3. And that gives me a pH of 2.74. Awesome. So we are done with part A. In part B, we're going to calculate the percent ionization of hydroxylic acid. So remember that the percent ionization, the percent ionization is defined, is the same thing as the percent dissociation, and is defined as the hydrogen ion concentration at equilibrium divided by the concentration of the acid initial, the initial concentration. And times 100 in order to make it a percentage. Of course, we already found the hydrogen concentration at equilibrium. That was this value up here, the 1.8 times 10 to the negative 3, which was equal to x. So we're gonna come back here and add that information. The hydrogen ion concentration is 1.8 times 10 to the negative 3 divided by the starting concentration. We go back to the beginning of the problem, we can see that the starting concentration was 0.175 molar. That's actually what we had put initially on our ice chart. So come back here, 0.175 molar and times 100. And that provides us a percent ionization or percent dissociation of about 1.0%. And we're done. Happy, happy people. All right, let's come back to the presentation. From there, here I wanted us to talk about the relationship between the percent dissociation and the molarity of an acid. In the problem that we just did, that's actually exactly this first row. We had an initial, oops, sorry about that. We had an initial concentration of the acid of 0.175 molar. We had said that once that acid dissociated, we ended up with a hydrogen ion concentration at equilibrium that was 1.8 times 10 to the minus 3 molar and a pH of 2.74 and a percent ionization of 1.0, right? That's what we just calculated. If we had done the problem again, but with a lower concentration of the starting acid, we would have obtained the values that are shown here. Notice that the hydrogen ion concentration would have been smaller. Because of that, the pH would have been higher because a higher pH means that we have a less acidic solution. But notice that the percent ionization actually increases. So this is a relationship that I want you to remember. As the concentration of the weak acid increases, the hydrogen concentration at equilibrium is going to increase. The pH is going to decrease, And the, well, it's going to decrease because now you have a more acidic solution. And my computer is dying, it doesn't let me write. And finally, the percent ionization is going to decrease, okay? All right, the next two problems are problems that I actually want you to do at home. And I'm gonna give you the answers so that you can check yourself. I will also post the solutions online for you to check each step, just in case that you have any problem. For part A, I got the answer to be Ka is equal to 1.5 times 10 to the negative 5. That was a 10, come on. And then for part B, the percent ionization or percent dissociation ended up being 2.75%. All right. The next problem you will also do yourselves. And the answer for part A ended up being a pH of 3.41. And the percent dissociation ended up being at 3.9%. The next part is talking about polyprotic acids. So a polyprotic acid is an acid that has more than one ionizable hydrogen atom per molecule. For example, something like sulfuric acid or phosphoric acid, which have 2 and 3 hydrogen ions that can be donated respectively. Each of the polyprotic acids is going to ionize in individual steps. In each step, we're going to be losing or donating one proton. So for example, here we have phosphoric acid with all of its 3 hydrogens. On the first ionization step, it is going to be donating one proton to become H2PO4 minus. In that process, it donates the proton. That proton is going to associate with water to form the hydronium ion. The second step, we're going to take the product from the first ionization, which is the H2PO4 minus, and that one is going to donate one more proton, becoming now HPO4 2 minus. Again, that proton is donated to the water, and so water becomes hydronium ion. Finally, for my third dissociation step, I'm going to take the product of the second dissociation, and I'm going to write it here. And then that HPO4 2 minus is going to donate the third proton in order to become phosphate ion, PO4 3 minus. That proton gets associated with water in order to form the third hydronium ion. Each of these steps, each of these ionization steps is associated with a respective Ka. So we have Ka1, Ka2, and Ka3. And I want you to notice the values. Notice that they decrease at every step, and they decrease quite significantly. What this tells us is that for each successive proton donation, it actually gets a lot more difficult to do than the previous one. So the smaller the value, that means the less that equation goes to the right. That means the more that the initial acid, it stays in the acid form, right? So the first donation is a little bit easier. The donation of the second proton is more difficult. The donation of that third proton is much more difficult. Here we have a list of a number of polyprotic acids. Notice that all of these have more than one hydrogen that can be donated. And each of the hydrogens that can be donated has a respective Ka. So Ka1 will be for the first donation, Ka2 will be for the second donation, Ka3 will be for the third donation if the acid happens to have 3 acidic hydrogens. Notice that for any given acid, the first Ka value is bigger than the second, and if there is a third proton donation, that third Ka is going to be even smaller than the previous two, right? I don't need you to know any of these numbers. I just need you to remember that the Kas decrease as you go from the first to the second to the third. And I need you to understand that the Ka1 is associated with the first donation, the loss of the first proton. The Ka2 is for the loss of the second proton, etc. Okay. So the rule for dealing with polyprotic acids. If the ionization constants, meaning the Kas, of 2 successive ionizations differ by a factor of 1,000 or more, 1,000 is 10 to the 3, basically. If it's 10 to the 3 difference between those two or more, then we can ignore the second ionization or the third for that matter in the calculation. And that's written right here. So if the ratio of Ka1 to Ka2 is greater or equal than 1,000, then we can go ahead and neglect the second dissociation and just deal with the first one. We're not actually gonna do much of those calculations, but you are able to see those in the book. But let's go ahead and do just a simple example. Oops, sorry about that. Write the reaction and the expression for Ka3 for phosphoric acid. So Ka3 for phosphoric acid. That means that we're looking at the third dissociation from phosphoric acid. And we know that phosphoric acid is H3PO4. Once it donates one proton, it will become H2PO4 with a charge of -1 because it has lost a positive charge that went out with that H+. The third dissociation is going to be what? What is going to be the donation of another proton, so it will become HPO4 with a charge of 2-. Going from H3PO4 to this one, that's associated with Ka1. Going from this one to this one, that would be Ka2. And so now we're going to deal with Ka3, which is going to be to take this, which I'm going to call HPO4 2-, which is going to dissociate partially into H+ and PO4 3-. Okay, that right there is associated with a Ka3, and that's the one that I need to write. So the expression for Ka3 would be equal to my products divided by my reactants. In this case, the product is H+ times the phosphate ion, PO4 3-, divided by the concentration of the acid on the left-hand side, which in this case is HPO4 2-. That's it. We are done writing the expression for Ka3. All right, so just to summarize, whenever you're dealing with a weak acid,